Hi, I'm Mike Barley with Electric Lab. This presentation is on the subject of electrical control systems. And this is our third edition of the book called Industrial Electrical Control Systems. We now have a fourth edition, and we've changed our title just a little bit, and now it's Electrical Control Systems, a little bit shorter, really gets to the point, you might say. And so this presentation is basically covering the first several chapters, which include electrical control systems basics, ladder logic elements, control relays, transformers, timers, reversing motor rotation. And then, of course, I would assume you're using some of our training equipment, the EL360 or the EL430 control trainers. And this would be the guidepost that's going to take you out into the lab and be able to get started doing some control systems wiring. So let's get started on building that foundation. Okay, here we go. So in electrical and industrial control systems basics. Section 1 is the three types of electrical control systems. The three types of electrical control systems. Manual, a system that requires human interaction to initiate the start process. Semi-automatic, a system that requires human interaction to initiate the start process but does not require further interaction to continue. So the example here is a dishwasher where you can hit a button and then it gets started and then it operates by itself from that point on. The previous slide was just showing you what is called a selector switch, and you physically turn that on and then whatever the machine is being operated, it immediately starts. And automatic, a system that requires no human and can start, complete, and stop a process completely by itself. And then, of course, our example here is a thermostat that as the temperature raises, it's going to kick on your air conditioning, cool it back down, and then when it gets warm again, bring it back up, that sort of thing. Does that all automatically. The sequence of operation. The sequence of operation is the step-by-step moves a machine makes to perform a given task. And there are three components of that task. The input, where there is obviously oftentimes human interaction, the logic, and then of course the output, what actually happens. Input means that the machine has received the signal to begin the task. And we have the example here of a start button. You hit that, the machine starts. Logic is the point where the decision is made as to what task is performed. And there's an example here of some logic. That's ladder logic, you would say. And once you've actuated a button, or perhaps a thermostatic control has reached a certain temperature, then it's going to begin working its way through the ladder logic and reading it and creating the proper operation. And the output is when the task is actually performed. In the example here, somebody hits a button and that begins the operation of that conveyor belt, like in an airport, and luggage is thrown on it, keeps it moving until somebody hits a stop button and that conveyor belt stops. Now, input switches, basic types, and functions. So there are two basic types of contacts, the normally open and the normally closed. And you can see in the examples here of the symbology on the left there, the open, where you can see clearly power is not flowing through it, and then closed, where the arm is down and actually making contact and power is feeding through it. So a force must be applied to actuate the switch contacts, and this will change the state of the contacts to closed or opened depending on their normal condition. And as you can see in the examples of symbology here, you have the one on the top there which says no, or normally open push button. You have to push or make a force, as it said, push that button that will make those contacts. The one below that, the NC, or normally closed push button, the contacts are already connected together In other words, they've already made contact, so when that circuit's energized, if there was a light connected to it, it would automatically come on, and then when you push that button, it's going to disconnect it. It is the reverse. Manual switches. There are many types of manual switches. Two common types are push button switches and selector switches. Emergency stop switches. These switches provide immediate opening of a control system circuits in an emergency, and the contacts are normally closed on an emergency stop. Typically provide an all stop to a process. That's hence the title emergency. Sometimes that's the case where it's on a piece of equipment that when operating, it needs to be turned off quickly because, something bad's happened. There's an accident or, some piece of equipment is malfunctioning. You hit that emergency stop, that's going to shut it down. Now, section 4, outputs and their functions. And I like this slide because it has an example of a great example of control logic. For example, what do you see at a railroad crossing? Well, you have the lights, obviously, like they show here in the picture on each side of the track, indicating that a train's coming. When that switch in that logic, probably up a ways up the track, realizes that the train is coming, or it trips and that knows the train is coming through, it automatically turns on those lights, and then they will operate until the train is gone, and then another set of contacts is actuated and then would turn off the lights and raise the arms on the tracks. Outputs and their functions. An output is the result of an actuated input. Outputs can be indicator lamps, the coil of a relay, a solenoid, or many other components. Now, section 5, ladder logic and diagrams. A schematic is something showing the main parts, usually in the form of a simple drawing or diagram. A schematic diagram is a drawing showing all components, parts, or tasks of a circuit device, flow process, or project by means of symbols. Ladder diagrams are used to depict the operation of the control circuitry. They arrange the inputs and outputs in an organized format, just like the rungs on a ladder. As you can see in the example here in this picture, you have on the left, this is L1, and on the right would be L2. So L1 is typically your energized part of the circuit, or the hot, and L2 will be your neutral. The power source is indicated by the vertical lines on each side of the diagram. The left vertical line, or L1, is the power side, or current carrying conductor, and the right vertical line is grounded conductor, also referred to as L2. The core components of a ladder diagram are power supply, conductors, input devices, and output devices. The core concepts of proper ladder logic design are: all rungs must be numbered, all components must be labeled, and only one load per rung. Only control devices are to be shown. All input and output devices must be in their assigned locations from left and right. And that is basic ladder logic. Some of those rules get bent a little bit once you move into a more advanced level of control logic in the realm of PLCs, or programmable logic controllers, but for our teaching in this particular scenario, this is correct. And here's a couple examples. Here's the one on the left. That's the correct diagram. You have an input on that first rung, and then a branch coming off of it, energizing the second rung. So you hit that input on the left there, close those contacts. It's going to energize output 1 and output 2. On the other hand, the diagram on the right is incorrect because it has them essentially wired in series, and that is incorrect wiring. Ladder logic and diagrams. When PB1 is actuated, coil 1 is energized, which actuates CR1 and de-energizes lamp 2. And here's our example. So you push PB1, that energizes the coil in CR1, and then the contacts on CR1 and rung 2 are closed. That's why it's showing as it's closed, and that energizes lamp 2. Now, ladder logic elements. This is a segment that I want to emphasize that knowledge of these and understanding these will really be very helpful for you as you move into the physicality of wiring control systems logic. The 6 elements of ladder logic, you should really try to memorize what these are. So, our first one is AND logic. And AND logic means you will press PB1, light won't come on. You press PB1 and PB2, then the light will come on. That is what you would call a two-handed switch. And as you get into the wiring exercises in our book, then you will see that the first several wiring scenarios are essentially all of the 6 elements of ladder logic. So you not only hear the teaching we're providing now and see the visual of the rungs, but then you'll actually see the physical wiring and what happens when you press the buttons in the appropriate manner, as they say. Now the next one is OR logic. This means that if I push input 1, output 1 will come on. And then if I push input 2 instead, output 1 will also come on. It does not take both of those for it to operate. It's input 1 or input 2. This is called NOT logic. So as you can see, input 1 is a normally closed set of contacts. So if I energize the circuit that's feeding L1, then immediately output 1 is going to come on. The light will come on. So then when I actuate input 1, I hit the button, as in a emergency stop button, for example, then that would actually de-energize the output 1, we'll say indicator lamp. Not logic. This is what is called NOR logic. So we have input 1, which is normally closed, and input 2, which is normally closed, and output 1. So when this circuit is energized, once again, immediately the light's going to come on. But if I actuate input 1 or input 2, that's going to break the circuit and turn the light off. And this is NAND logic. So we have 4 total normally closed contacts. So let's say you have a 4-door automobile and you have a dome light in the ceiling of it. So you got 4 people getting in the car. Once the doors are open, the first door gets shut, the light stays on. The second door gets shut, the light stays on. The third door gets shut, the light stays on. When the 4th door is closed, that opens the entire circuit and the dome light goes off. And finally, the seal-in circuit. This is essentially one of the key wiring scenarios in the lab that you'll do. Wiring a seal-in circuit, commonly used for what are called start and stop stations, provides wiring that you have coming from the load side of the stop button through the auxiliary set of contacts or the secondary contacts used to seal in or close this circuit and hold it, and then comes out of that set of contacts to the load side of the start. So the only thing that will break this circuit once that's sealed in is to hit the stop button, and that will open up the circuit. This is another one that really, until you've actually wired it and have the understanding of how it's wired, this is really one you just have to see. Section 16, control relays. A control relay in an electromechanical device which activates multiple poles when current is delivered to its solenoid coil, resulting in the closing or opening of the pole contacts. So we have 2 basic types. We have the machine control relay, and at the bottom here we have the general purpose relay. The machine control relay, aka a contactor, multi-pole contactor. And you can see if you look closely at this photograph, there are contacts on this one that are NO, or normally open, and there are contacts on it that are normally closed. The general purpose relay aka an ice cube relay. And you can see why they would call it an ice cube. And it's all just a clear plastic box around the contacts inside of it, to where you can actually see the operation of this type of relay as you're energizing it. Section 18, magnetic motor starters. So first of all, let's talk about what a motor starter is. On the screen here, you see three pictures. The first one is a contactor plus a set of overloads. When you connect both of those together, screw them both together, on the right you see what is a motor starter. This is kind of a smaller version. Again, on our trainers, you're going to see kind of a standard motor starter, 20 or 30 amp capability, I believe it is. I've seen motor starters that were probably 18 inches tall and maybe 12 inches wide. They were huge. Just all depends on what the ampacity is of that device. But it takes those two components to make a motor starter. Section 19, controls transformers. Now, a control transformer is typically used when you have a power supply that is coming into an area and you need to drop it down because you want your control wiring to be at a lower voltage. Oftentimes we do that to create a scenario where we have control voltage operating at a lesser voltage to create a safer work environment. Obviously, when you can drop the voltage at any time from maybe 480 volts or 277 volts down to 120 volts or even maybe down to 24 volts, that's going to create a lower voltage and in essence create a safer environment around those conductors and conduits or what have you. The power supply typically being provided for industrial control circuits will be reduced by using a step-down transformer or control transformer. Section 21, timers. Timers control the sequence of events or a process that requires a delay or a timed actuation of contacts or loads. A time delay relay is essentially a machine control relay with a timing device attached to its coils and contacts. The core components are a coil, contacts, and timing device. This device that you see here is essentially a general purpose relay or ice cube relay, only it's not clear, but it does the same thing, only it has a timer attached to it there at the top, fixed at the top of the device, to where it is a general purpose relay that operates with a timer. On delay. When an on delay timer's coil is energized, the relay's timing mechanism begins to run, but its contacts remain in their normal state. When the preset time is reached, the contacts then move into the state opposite of their normal state, normally open or normally closed. They will remain in that state until they are de-energized. After reading all of that, this is the reason why you use the training equipment, because reading this to you versus actually seeing the physicality and the results of what happens when you wire a timer makes all the difference in the world. That's why you have so many wiring scenarios in our lab book, because it would be far more easier for you to take in and retain the knowledge of how a timer works if you've wired it several times. That is the idea of our training. Off delay. When an off delay timer's coil is energized, the timer's contacts immediately move to their energized state. But the timing mechanism does not operate until the coil is de-energized. Once the coil is de-energized, the timer will begin running until the preset time is reached. Then the contacts will return to their normal states. Timers are available in a variety of types. The type used in this publication is used for process, machine tool, and safety control, among other uses. It is mounted on an 11-pin base and typically attached to DIN rail. The product that we use on our trainers is a MS4SM, is I believe a Fuji brand, and we purchase those from Automation Direct. And if you get on their site, you'll see a wide variety of different types of timers. We use these because we believe these are a great entry-level version of a timing device, easy to learn on. Now, this slide is showing you the 4 settings that you'll see on the timer, and it gives you the terminal numbers for all of those timers. And I believe, yep, on our next slide here, we're showing where all of the contacts are. So up there at the top left, we'll just use that because they're all the same. It's just a matter of if you set the timer on a different setting from on delay, flicker, one shot, sign off delay, all of those. So power goes into the coil at number 2. Number 10 is the neutral feeding to it. Then the start signal, 2 and 6 are actually pre-jumped together on the control trainers that we sell. And now under timed NC, that means the terminals 1, power goes in and goes out 4. That's the set of contacts that are being timed as a normally closed contact. 1 and 4 and 11 and 8 are normally closed contacts. Normally open contacts are 1 and 3 and 11 and 9. Section 24, reversing motor rotation. So the rotation of a three-phase motor can be reversed by switching any two of the three-phase conductors supplying power. The NEMA standard for this procedure is to switch A phase and C phase. So why would I want to reverse the rotation? Well, for example, if you were creating an operational process or a process in a manufacturing plant where you needed something to turn in a certain direction and then stop and then reverse, maybe it's a conveyor belt, could be a variety of different things. I know this when you're installing. I used to do a lot of work in restaurants, and if you were installing an exhaust fan motor on the roof of the building to suck out from air out from the kitchen, if you wired that three-phase motor and fired it up and it was rotating in the wrong direction, it might be sucking air into the restaurant instead of sucking it out. Well, I'm going to tell you how to fix that problem. A reversing motor starter has the ability to transfer the phase conductor safely by using an interlock to prevent collision of phases and a reversing kit. When one coil A, is energized, rotation will be in one direction, clockwise or counterclockwise. When the other coil B, is energized, rotation will be in the opposite direction. Rotation reversing can also be done via a drum switch, which basically is a device, as you see in the graphic here, that is showing poles that are being switched inside of that switch to reverse those directions, reverse those phases like we showed you earlier to create that opposite direction. Drum switches accomplish the reversal of the phase conductors by mechanical means internally in the switch. Now, section 26, manual mode, automatic mode, and HOA. So manual mode requires human interaction. That button's not going to push itself. You have to push that button yourself to make something happen. Automatic mode is initiated by the press of a momentary contact. Handoff automatic, when actuated, will immediately energize a load. Off position blocks all power. And this is, again, one of the scenarios that is in the book. There's a reason why you would need this in a manufacturing process. So that's why we have those specific wiring exercises in the book. And that concludes our teaching on the basics of electrical control systems. So now that we went through all of the core principles and ladder logic and all of the items regarding inputs and outputs, or at least the basics of them, I should say, now it's time to get into the lab and start working through some of your wiring diagrams. And our wiring diagrams in this book will take you from the basic 6 elements of ladder logic all the way up to reversing a 3-phase motor. If you're using the EL360s, then you're going to have a book that has a reduced amount of scenarios because you're going to be only able to do things that are 120 volt, because on those smaller trainers you only have a small motor instead of a 3-phase motor. But as you go through those, make sure that you take time to not only just work your way through the scenario, but understand what the logic is telling you and what it is doing when you see the scenario in operation on the trainer. Oftentimes I see students that go through this and then just feel like it's a competition with the other students to see how fast they can get through the wiring scenarios and don't really take the time to see what is happening. As you go through using an on delay or an off delay or the flicker setting on the timer, stop and watch the scenario operate as you've energized it and allowing it to work to see what functions and how that works, so you'll retain it better if you'll do that. So All right. Well, thanks for watching. My name's Mike Barley with Electric Lab, and hope this has been informational for you. And let's get to work in the lab.